take a look at this diagram. This is a good sketch of an extruder screw in in a barrel, and it defines some of the parameters. And so the parameters we have here are the diameter. Notice it's the inner diameter of the barrel. This is a little bit greater than the outer diameter of the screw flights. And by the way, they are missing a possible parameter. There's a gap between the flights and the barrel. The gap is small. It is an opportunity for polymer to leak, but if we have high viscosity fluid that we're moving through this system, it is better to not have these components rub against each other. We can use the high fluid viscosity to act as a kind of dynamic seal so that the leak through this gap is not significant. But in this case, for this particular model and sketch, this gap is not a significant parameter. We have the width between the flights from one flight to the next. We have the height of the channel, and so the width and the height define this cross section that is the channel that the fluid flows through. And then we have phi, the angle of the flights. And I would guess that n must be the RPMs. Let's take a look at down for a minute. Okay. Rotational speed n, yes. Anytime I have something with time, I would like to put a notation of an n dot that tells us that it's some kind of a rate. But that would be turns per second. N could just be 50 turns, but whether it's happening in a second or an hour. We'll go with his notation, but I just want you to know that it's probably better to put time rate things, put a, I don't know if I can do that, put a dot on top of it. Nope, I can't do that. So, all right. Very good. Shear strain rate through the height of the channel. So that leads us here. And so we can get this velocity, the relative motion, is pi times the diameter times the turning rate, rotational speed. And they put the subscripts I here because we can say that I is 1 for the pilot process and 2 for the scaled up industrial version. Okay, so it would tell us what the velocity is for the new scaled up extruder. Now the volumetric throughput, and really this is what we're interested in, is volumetric throughput, because this determines whether the system's profitable or not. It's the cubic meters, or if you want to say cubic centimeters of polymer we can produce per unit of time, volumetric flow rate. And just geometrically, it's this velocity. So the velocity has one length unit in it, it's length per time. And so then this is the material flowing through, I should use my pencil for better control. It's a material flowing through at U naught, flowing through this window that's H high and W wide. And so that gives us the total volumetric flow rate. Because this is happening at an angle phi, we have to account for cosine of phi to calculate the correct volumetric flow rate. Now we can substitute in for this velocity, and so we see that a volumetric flow rate, we have the geometric factors of pi and cosine phi, but it's controlled by the diameter, by the turn rate, by the height of the channel, and by the width of the channel. So if we want to increase the flow rate, we need to increase as many of these parameters as we can. We need to make the diameter as big as it can get. We need to make the rotation rate higher. That increases pumping. We need to increase the channel depth H and width W, because then that means there's more material flowing through. So it's pretty straightforward. But we have to do that within the limits we discovered from the pilot process.